Operational amplifiers as integrators. Hello everyone, my name is Rafael, I'm an electrical engineer, and in this video I would like to debate with you the topic of operational amplifiers as integrators. Firstly, I'm going to show you the theory and subsequently the solution of an exercise. Let's do it. The first step here is to comprehend the operational amplifier connected in the inverted configuration. It's possible to demonstrate that the transfer function of this configuration is of the sort T of S equal to the output voltage in the complex variable divided by the input voltage. We wish to express the transmission with respect to the impedances. Then it is going to be the negative of Z2 divided by Z1 of S. Okay? Using this configuration, we can implement the integrator. This is the integrator. Notice that between points A and B, there is a short circuit. Okay? A virtual short circuit, not physical, virtual short circuit. Then the current I1, this current here, the current I1 is equal to the input voltage Vi of t divided by this resistance here, okay? Because this voltage here is equal to the voltage drop here plus this voltage here, which is 0. Then the current is this. Alright? Now we are going to calculate the capacitor voltage. The capacitor voltage can be written as Vc of t equal to Vc plus 1 over C times the integral from 0 to t of I1 of t dt. Okay? This is the capacitor voltage. And as V0 here, the output voltage, is the negative of the voltage across the capacitor, as V0 of t is equal to the negative of Vc of t, then we find that V0 of t to be equal to the negative of Vc minus 1 over C, the integral from 0 to t of I1 of t dt. Next, we are going to substitute here in I1 of t, we are going to substitute this. And lastly, we find that V0 of t is equal to minus Vc minus 1 over Rc from 0 to t of Vi of t dt. This is the voltage across the capacitor from 0 to t. Okay, assuming that at first the capacitor has a voltage Vc. This is the initial condition. We can set the initial condition to be equal to 0, but we are considering everything here in the theory. Lately, in the exercise, we are going to set it to be 0. Okay. This is called the Miller Integrator. This. Miller is a guy that worked with this in the beginnings of electronics, and it is called Miller Integrator. This circuit provides an output voltage that is proportional, the output voltage is proportional to the time integral of the input is proportional to the time integral of the input voltage, with Vc being the initial condition of integration and Rc the integrator time constant. This is the time constant of the circuit. Now let's express it all in the time domain. I am going to erase this. Okay, we just did that. We expressed this in the time domain. Now what we need to do is to express the same in the frequency domain. In the frequency domain, here Z1 is equal to R. Okay? Z1 is R. And Z2 is equal to 1 over Sc. And then the transmission in the frequency domain is going to be T of JW equal to minus 1 over JWRC. Okay? We've substituted S by JW because for physical frequencies, S is equal to JW. Now let's inspect this. To fully comprehend the circuit, we need to inspect this. Let's inspect the magnitude. Let's inspect the magnitude. The magnitude of the transmission is the magnitude of V0 divided by Vi, which is 1 over WRC. Okay? This is the magnitude. You can see here, as we increase the frequency, the magnitude decreases. Now let's take a look at the angle. Obviously, we have an imaginary number here, then the angle of the denominator is 90 degrees. And then we pass to the numerator, it becomes a negative 90 degrees, with this negative sign here, positive. So the angle is positive 90 degrees. And we can plot a graph here. Okay, by a frequency in the logarithm, and here the magnitude. We're gonna have something of the sort. And here is the frequency of the integrator 1 over RC. This is the frequency of the integrator. Wint is the inverse of the time constant of this. Is the inverse of the time constant of the circuit. It's called the integrator frequency. And an integrator behaves as a low-pass filter. You see that it behaves as a low-pass filter because at DC the signal passes, but at the high frequencies the circuit attenuates the signal. With a corner frequency of 0. The corner frequency here for this magnitude is 0. Okay? Now let's go to the exercise. This is the theory Subsequently, we're going to go to the exercise. The exercise is going to be based on this theory that I just demonstrated to you. The exercise, letter A, find the output produced by a Miller Integrator in response to an input pulse of 1 volts height, 1 volts height, and 1 milliseconds width. The pulse is going to be of the sort, I'm going to show you the pulse, how the pulse looks like. VI and VT. The pulse is going to be of the sort. And here, 1 milliseconds. So the height of the pulse is 1 volt and the width of the pulse is 1 milliseconds. This is what the exercise wants us to consider in letter A. And letter R, the exercise wants us to consider R to be 10 kilowatts. 10 kilo ohms, and the capacitor here 10 nanofarads. Okay, this is what we're going to work with, and let's solve it. We are going to use this circuit here. Okay, in letter A, we want a response for a 1 volt, 1 millisecond voltage pulse. Okay, as we did before, the output voltage here, based on the formula that I wrote here, is going to be V0 of t equal to the negative of 1 over RC, the integral from 0 to t of 1 volt dt, of 1 volt dt. And the t here, we are going to integrate from 0 to 1 milliseconds. Okay? And for us, the initial condition is 0. Vc is 0 volts. Okay? For C equal to 10 nanofarads and R equal to 10 kilo ohms, we calculated the time constant of the circuit to be equal to RC equal to 10 kilo ohms times 10 nanofarad, and this gives 0.1 milliseconds. We are going to substitute these values here, and then we find that V0 of t to be equal to the negative of 10 times the integral from 0 to t of dt, and if we conduct this integration, the final response is going to be negative 10 times t. Okay? This is the response from from 0 to 1 milliseconds. The output voltage reaches a magnitude of negative 10 volts at 1 milliseconds and remains constant thereafter. I'm going to draw it for you here. I'm going to draw it for you here. Okay, this is how the output is going to be. Okay, here 1 milliseconds, and here negative 10. It's going to go from here to here, and then it is going to stay there. Alright? The output voltage is not going to return to 0. The output voltage is going to stay at negative 10 volts. This is a problem. This is a problem we need to deal with, because we wish the output voltage to return to 0. How can we do this? How can we make this happen? We are going to implement the exercise of letter B. Okay? In letter B, we are going to fix this problem. Let me raise the heat. I'm going to show how to fix this problem and make the output return to 0 when needed. In letter B, the exercise says if the integrator capacitor is shunted by a 1 mega ohms resistor, we are going to connect a resistor here. In parallel with the capacitor. And this resistor, RF, is 1 mega ohms. And the op amp is specified to saturate. It is going to saturate at plus minus 13 volts. Okay. You are going to see that the output voltage is going to return to 0. And the 1 volt pulse will provide a constant current of 0.1 milliamperes at the output. Okay, the output current is going to be 1 volt divided by 10 kilo ohms, which is equal to 0.1 milliamperes. This is the output current that's going to go here. All right? We're going to use this value of the output current. And now, to find the output voltage, we will use the following equation. V0 of t is equal to V0 of t going to infinity minus V0 of t going to infinity minus V0 of 0 plus times E T RF C. Okay? This is V0 going to infinity. There is a bracket here. This is V0 going to infinity. This is V0 going to infinity. And this is V0 of 0 plus. And the output voltage for t going to infinity, we are going to calculate this first. V0 of t going to infinity is going to be equal to the output voltage, the output current that we just calculated, 0.1 milliamperes times 1 mega ohms, okay? And this is equal to negative 100 volts. And the output voltage at t equal to 0 plus is simply 0. V0 of 0 plus equal to 0 volts, okay? Because we got a capacitor here, the voltage across the capacitor does not change immediately. Then at 0 plus, the voltage across the capacitor is 0 volts. And the output will be an exponential. The output is going to be an exponential heading towards negative 100 volts with a time constant equal to, let's calculate the time constant. This is the time constant. RFC is equal to 10 nanofarads times 1 mega ohms, which is equal to 10 milliseconds. This is the time constant of the circuit, 10 milliseconds. Okay, I'm going to erase it here to show you the final solution. The final solution will be V0 of t equal to negative 100, 1 minus e t divided by 10 from 0 to 1 milliseconds. Okay? The exponential will be interrupted. The exponential will be interrupted at the end of the input pulse. At the end of the input pulse, the exponential will be interrupted. And we reach the final value of, let's calculate the final value of the output voltage. It is going to be equal to minus 9.5 volts. And then another graph here. This is the graph for letter A, and this is going to be the graph for letter B. Here, instead of negative 10, it is going to be negative 9.5. And instead of being linear, as in here it is a linear line, instead of being linear, it is going to be an exponential. It is going to be an exponential. Okay, here 1 millisecond, and then it's going to fall here as an exponential, and it is going to return to 0. Okay? The difference is that here the output voltage does not return to 0, but here the output voltage returns to 0 because there is a resistor here, and the voltage across the capacitor is going to pass through the resistor, and it's going to consume energy. And slowly the capacitor is going to lose its voltage. Okay? So here it stays where it is, and here it returns to 0. Okay, my friends, this was the video that I wanted to make. I hope you guys learned from it and enjoyed watching it. I am a teacher. If you guys want to book a lessons with me, use my WhatsApp number, guys. Goodbye.